everyone. Today we are discussing about very important and interesting topic and simulate them. So our today's topic is simulate the converging diverging nozzle, and we are investigate the variation of Mach number throughout the surface of our nozzle. So I always try to give some basics before the simulation. So I so you can see my slide here. So there are two types of nozzle. One is converging nozzle where the area are gradually decreasing, and another one is the diverging section when the area of the nozzle is gradually increasing. So we all know that there is Mach number, and Mach number are varies from 0 to high. So when the Mach number, we know that when the Mach number is less than 1, that is subsonic flow. And when the Mach number is higher than 1, that is the supersonic flow. So in our simulation we are investigate that the Mach number is lower in the subsonic nozzle, or means the converging section, and Mach number is higher in the diffusing section or diffuser section, and investigate the variation of this Mach number. Also, we also investigate the temperature variation and pressure variation along the throughout the surface. So in our model, we are chosen here to compressible flow, where the density is changed significantly changed with the pressure and temperature. So let's talk about our geometry. So at first, I open the workbench simulation software. In the geometry section, we are create a converging diverging nozzle surface, and then we are simulate here or apply the boundary condition and finding our main result. So that is my window of workbench. So we always use the fluid flow fluent. Okay, so go to the geometry section. We use design modeler. Here we create our geometry. So basically, we created a random converging diverging nozzle without neglecting the actual measurement or actual dimension. So here, normal we sketching from line sketch. So uh, that is our origin. So we start from here. Okay, this is vertical line. Then we created a gradually cross section decreasing cross section, that means a converging nozzle, then created a throat, then I created a diverging section here. Okay, then I goes into the vertical section and connect this point is this point. Okay, so to constrain, we almost complete our geometry to constrain and coincide. So this point, this line and this line are coincide. This point, okay, and almost done here. So geometry. Then we modify surface from sketches, from concept, surface from sketches, and sketch one, then generate. So that is our surface geometry, and material we are chosen here to frozen. So generate. So mainly we when we use the fluid flow model, so our geometry is always, our full domain is always fluid domain. So here you see the domain is default by default in solid domain, so we change the solid domain into fluid domain. So we change fluid domain, then generate. Okay, So our domain is fluid domain, and our geometry is look like this. So okay, then go into the our meshing. So in meshing section, uh, so our meshing is so much normal because geometry is very simple. So that would be gives us very accuracy, higher accuracy for finding our agent. So okay, here you see our geometry here. So in the digression, so here is our converging diverging nozzle. I actually use here the random geometry here. The this section and this section are length is variation, so it doesn't any discontinuity in our agent. So that's normally generate. So we default use here the element size is 100 because it gives much accuracy in my result while the PC is lacking. So I choose element size is 100. So we also okay, this is fine. So we also named our selection. So this edge we called the inlet. So the air inlet from this section. So this is our inlet section, and this is our and this section is our outlet section. So OLT and it outlet. Okay. And this line control this line, and this line. These four lines is our wall section. So this is our wall. So we named all the selection. Let's check the name selection here. So this is our inlet, this is our outlet, and this four line is our wall. So okay, our finish mesh is complete. So let's update the mesh. Okay, let's dive into our important section, that is setup section. So we choose setup section here, and enter the setup section. We use don't need to double precision because our simulation is too much easy. So okay, so in our okay, let's go into our general geometry import. Okay, geometry is completely import here. So in our general section, so we basically used here solver type is density based type because we know that our flow is compressible flow where the density is huge variation with temperature and pressure. So we use here a density based solving problem. So then go into the model, and we use here energy equation because temperature and pressure are hugely significant for the compressible flow, and here we change the Mach number variation, so we must need to the energy equation here. Also in our viscous model we use inviscid model because you know that in aerodynamic shape where the Mach number is higher than 1, where the viscous flow is negligible and the Reynolds number is so much higher, so that's why we use here in okay, electricity is gone, so that won't work. So okay, let's talk about our material. So we used here for our fluid is a air. So you must change the density from constant to ideal gas. So we change our geometric density here. Okay, then close. So let's talk about our cell joint condition. So you must care about it because normally the material is assigned as AR default. So you must change when you used different type of air. So here air is by default. So okay. Let's talk about our boundary condition. So, due to our compressible flow, we must need add an inlet for pressure inlet. So here we use pressure inlet. So Gauss type total pressure, we use a random pressure. So that is 500 megapascal. So that is 500 500,000. Okay, as a thermal that we are use here the temperature as a 27 degrees Celsius. That means 300 Kelvin. So that is our inlet boundary condition. Also, at outlet we use pressure outlet, and the gauge pressure is we use the atmospheric pressure. So 101,325 Pascal, and close it, and the wall condition is normally wall. So we are done our boundary condition here, then go into the methods. So in method section we normally used implicit formulation. Then okay, we not need to change anyone. So in initialization we use hybrid initialization, then initialize our problem. So you see the our initialization is almost done here. So we almost done our work. So number of iteration we choose 500 iteration, then solve our problem. Let's solve it. uh, it takes too fast because our geometry is too much simple, that's why. So our main determination is the variation of Mach number, including in converging section and diverging section and throttle section. And we know that when in converging section, when the Mach number is less than 1, that is called subsonic flow. And when the Mach number is higher than 1, that is called supersonic flow. So we investigate that where in our geometry, where the subsonic and supersonic flow are occur. So let's go into the graphics, then contours. So in velocity contour and magnitude is Mach number. So magnitude is okay. Our simulation is almost done here. So let's check the result section. So we go into our contour. So contour of velocity, and the variation is Mach number. So here we see the Mach number. Okay, that is Mach number. So save and display. Okay, here's some problem. So in our results section, so we use contour for velocity, Mach number, and then display. So here you see our result section, and we see the inlet when the air is flow through the converging section, the Mach number is below the 1, that is indicated by blue color. And when the air is come into the throat, this is throat section, this section is throat section. So when the air is come this section, the Mach number is increasing, and this section is Mach number go into the 1, that is called choke condition. And when the air is passed through the diverging section, the Mach number is gradually increasing. So that's our main determination here, how the Mach number are vary throughout the converging diverging nozzle. So we use also the plots. So use plot here in. So our main determination is almost done here. So in this video we are see the variation of Mach number throughout the converging diverging nozzle, and we finally figure out the Mach number is less than 1 when the fluid are flowing through the converging section, and when the fluid are in the throat, that is Mach number is 1 and nearly 1 here. And when the Mach number is higher than 1, that is diverging section, that is indicated by red color. So that is our video here. So thank you for everyone.